different time domain specifications of a second order system, especially damped, underdamped second order system, right? If the theta lies between 0 and 1, it is less than 1, we can call it as a stable underdamped system. And the first important parameter which decides the performance of a second order system is the rise time, right? So how will you define rise time? The rise time is the time taken for the system response to reach 100% of the final value. Then we have derived the relation between rise time and damping ratio, that is pi minus theta by omega d, where theta is equal to tan inverse root of 1 minus zeta square divided by zeta. Now, then the second parameter was peak time. Peak time is the time taken by the response, the instant of time at which the output reaches the first peak of the output. Right. For an underdamped system, there will be overshoot present in the output response, right? There will be overshoot as well as undershoot. Overshoot means the portion which is going beyond the steady state value, and in the output response there will be exponential time as multiplied with sinusoidal time. So there will be a decaying sine wave, right, because of this exponential time. So finally at one time it will settle. Okay, so we are now deriving the magnitude of the peak time, so that what we have done, since it is the maximum value, we have differentiated the output response and equated to 0. Then we understand that T is equal to n pi by omega d. Okay. So since a lot of peaks are there, we need to find the global maximum of the function. What we have to do, again, we have to find the second derivative of the system, right? And so if you differentiate it again, you'll get e square y of t divided by dt square. So if you differentiate again dy by dt, what we will get? Dy by dt is equal to e power minus zeta omega t multiplied by omega d plus zeta square omega divided by root of 1 minus zeta square, right? Yeah. So if we differentiate, it's this one, this portion. Now we have to differentiate this portion again. So what we will get is, we also try constant, we can take it out, that is omega d plus zeta square omega n, the whole divided by 1 minus zeta square. So this is a constant, taking this one out. So again, if you apply differentiation, you will get minus zeta omega t multiplied by again minus zeta omega n. It is multiplied with sine omega t plus cos omega dt multiplied by e power plus zeta omega t into omega d. This one, right? So finally we will get e square e of t by dt square. So we will substitute this. We know at what time, at what time period, the first derivative is 0, right? At what time it is 0? It is t equal to n pi by d that we derived as a last class, right? This one. So at what value dy by dt is 0. So for this time period, we can write again d square y by dt square is equal to omega d plus zeta square omega n divided by 1 minus zeta square e power. So what about this part? First part, if you apply this time period n pi by omega d, because since it is sine, if you apply from this, you can find out omega d, right? What is omega d? Omega d is equal to n pi by t. So t will cancel. So sine n pi will come. So when n equal to 1, 2, 3, etc., this part will become 0. Only we need to write this part. So we can write this part as e power minus zeta omega n. And what about t? Instead of t, substitute n pi by omega d. Multiplied by omega d. What about cos omega dt? Instead of omega d, you can substitute n pi by t. So t will cancel. Finally, you get cos n pi. So now we have to see at what value of n d square y by dt square becomes negative. If it is less than 0, it will give the global maximum of the function. If it is greater than 0, it will become the local minimum. Whether we need global maximum or local minimum. In our case, because global maximum, right? So at what value of n it becomes -1? For n equal to -1, this one, or n equal to 1, it becomes -1 because cos n pi becomes -1. Means cos pi is -1, right? And what about the other values, odd values? For n equal to 0, 2, etc., what will happen? This time becomes positive, so we will give only local minima. So from this we can conclude that the peak time of a underdamped system is pi divided by omega d. And d is the damped frequency of oscillation. This relation keep in mind, because in numerical examples you have to use directly this equation. You cannot derive. And this also you keep in mind. Rise time is pi minus theta by omega d, where theta is tan inverse root of 1 minus zeta square by zeta, and both factors are dependent on zeta, right? Okay, one more thing. So another important parameter is called maximum peak overshoot. Maximum peak overshoot. Can be represented as capital M suffix P. What this indicates? Maximum peak overshoot. Again, I will draw this waveform here for an underdamped second order system. Let this be the steady state value y. So this can be written as y of infinity, right? Because this is the steady state value. Yeah. Now, if I draw the response, it will be like this. First, there will be an overshoot, sorry, then followed by undershoot, overshoot, undershoot, and the magnitude will reduce, and finally it will start at some point, steady state value. Right. So, what maximum peak overshoot is? How much magnitude it is exceeding from the steady state value. Okay. So, which is that part? If I draw in this. So this is our peak time, means time taken to reach this first peak, right? So this part, this is the overshoot, maximum overshoot. So how much the output response is going beyond the steady state value. Okay. So how can I calculate this? How can I calculate it? See, this is the point at which the magnitude is y of infinity. This is the magnitude corresponds to y of infinity. And what about this? This magnitude? Y of TP. Yeah, absolutely right. Y of TP. So we can calculate the maximum peak overshoot MP as Y of TP. The magnitude at peak value minus steady state value Y of infinity. So this can be expressed in percentage, means how much percentage it is exceeded. So that we can divide it with again 1 of infinity, multiply it with 100 in order to convert the percentage. Clear? Now we will substitute the values and find it. So that first of all we will find out what is Y of TP, because Y of infinity we know it is 1, right? What is the value of Y of TP? How will you find this? Yeah, correct. We know TP is equal to pi by omega d, and you substitute in the response and find what is the value of Y of TP. Because our Y of t is 1 minus e power zeta minus zeta omega nt cos omega dt minus again e power minus zeta omega nt sin omega dt into zeta divided by 1 minus zeta square. This is our relation. Now substitute Tp is equal to pi by omega d. So what will happen to the sine time if you substitute t is equal to pi by omega d?
0.
Yeah, that part will become 0. Then in our relation only cos term will be there. The cos omega dt, if you substitute t is equal to pi by omega d, it will become, so it will, and I will write this, that will be better, e power minus zeta omega n into t becomes pi by omega d and cos omega dt. Cos omega dt. Omega dt can be written as pi by omega d. Every other part is 0. The sine part will become 0. We don't need to worry about that. So this becomes 1 plus, because this and this will cancel. Cos pi is minus 1. So it will become e power minus. What is omega d in this? If you substitute omega d equal to omega n multiplied by 1 minus zeta square, omega n and omega n got cancelled. So finally you will get minus zeta pi divided by root of 1 minus zeta square. Right? So this will be the output value with respect to the peak time. Now how will you calculate MP? If you substitute this in that relation, you get Y of TP becomes 1 plus e power minus zeta pi divided by root of 1 minus zeta square. Again, minus Y of infinity. In Y of infinity is 1, the whole divided by, again Y of infinity is 1 multiplied by 100. So this one everything will cancel. Finally, we will get percentage MP. MP in percentage is equal to e power minus theta pi divided by root of 1 minus 80 square. This is an important relation. Keep in mind, multiplied by 100. So this is the relation for maximum peak overshoot. So if you know the damping ratio of a particular system, you can find all the parameters, rise time, peak time, even peak overshoot also. So if I increase, now you will see what happened to the MP. If I increase zeta, if zeta increases, what will happen to the percentage overshoot? From this relation, it will decrease or increase? Sorry? Yes, decreases, right? Because it is e power minus some theta time, right? So if damping ratio increases, MP decreases. Now you observe that rise time. If the same thing happens for zeta, what happens to the rise time, you see? Because the relation is pi minus theta divided by omega d, where theta is dependent on the zeta, right? Tan inverse root of 1 minus zeta square by zeta. So from that relation, it is understand that if we increase zeta, rise time will increase. This is observation, right? See, as a control engineer, our aim is to, we'll go to that waveform. Our aim is to reduce this overshoot, right? Not only reduce the overshoot, what about the rise time? Rise time also has to increase or decrease because we need to reach the steady state as early as possible, right? So as a control engineer, we have to reduce the overshoot and reduce the rise time. But if you see this, both are in opposite direction, right? If you increase zeta, you are able to reduce the overshoot, but you cannot increase more because it is affecting the rise time also. So there should be a trade-off between this TR and MP. Usually for common control system practice, we are taking zeta as design practice. Zeta value will be equals 0.4 to 0.8. So keep in mind. So this will be the which is just a thumb rule only. So if zeta is less than 0.4, what will happen? Our MP means peak overshoot becomes very high, right? If zeta is going beyond 4, TR will be very high. TR will be very high. That means we will get only sluggish response. So there is a trade-off exists between rise time and peak overshoot. Usually, actually, we will take zeta as 0.707. Okay, this we will discuss later. So this value keep in mind. Whenever, suppose next, anyway, final year you will do projects, right? So in that case, if you want to design a controller for a particular system, say a motor speed, you want to control, and anyway, you can select value between 0.4 and 0.5. We really should not select value more than that. That is the reason. Okay. So now we will move to the next important parameter. This is also very important parameter. It's called settling time. This parameter we have already seen in case of first order system. What do you mean by settling time and time constant? How you defined that? Settling can be denoted as t suffix small s. Okay. I think someone has joined, but I mistakenly rejected it. Who joined now? Have you observed it? I mistakenly rejected him. Someone else put comment. Some people are waiting to join. Yeah, because I am admitting everyone. Is any other students waiting? No, right? Okay, we'll continue. In case of a first order system, how you define the time constant? Time constant is the time taken by the response to reach 63.2% of the steady state value. And then you have seen that there will be a band to determine the settling time. Right? Settling time is the time taken by the response to reach the steady state. We have considered it as plus or minus 2% or plus or minus 5%, right? So likewise, here also we have a band. If I draw the waveform again, T, suppose this is my steady state value 1. I have a band, plus band and minus band. Let it be plus or minus delta. Plus or minus delta. So this can be written as 1 plus delta, and the lower one will be 1 minus delta. Plus or minus delta. This is the band. Okay. So how can we define the settling time of a second order system? Can be denoted as t suffix x. So ts can be defined as is the time taken by the output to settle within a band. To settle within a band, the band is plus or minus delta. So how can I draw the response in this? If I draw the response, it will go like this, and there will be oscillations. It will decrease, and finally it will settle some period, some value, right? So if we settle in this band, we can call it as the time taken to reach the so in this case, what is settling time? This is the settling time, right? Without any oscillation. So this will be the settling time. Okay. Now we have to find settling time in terms of the zeta or omega d. So how can we find this? And usually we have two bands, right? It will be for a second order system, we have considered as 2% and 5%. Likewise, here also we have two things. We have to obtain the settling time for two conditions. One is for plus or minus 2%, and the other one is plus or minus 5%. So how to obtain it? So how can we derive it? How can we derive it? Because we know the y of t is 1 minus e power minus zeta omega something like that, right? So from that relation, how can we derive this settling time? No, no, one we cannot put it right. So which term you will equate it? Whether you want to, you are telling correctly, with in y of t we have sinusoidal time as well as e power time, right? Exponential time. So which time we have to equate it? We don't need to equate everything, right? Because after settling time, there is no oscillations, right? So which time we have to equate? Yeah, which time we have to equate? We don't need to take all parameters. In that, the exponential time, that is the decay time, right? So which is the exponential time? E power minus zeta omega n t divided by 1 minus zeta square. This, if you equate to, what about plus or minus 2%? It can be written as 0.02. Clear? For 2 plus or 4 plus or minus 2% band, you equate this time to e power, sorry, 0.02. So this can be written as e power minus zeta omega n t s, here you can substitute s, which is equal to 0.02, approximately equal to. You can write like this. Similarly, if you take natural log, you can find out inverse, sorry, ts. So minus zeta omega is equal to natural log of 0.02. So if, what is the value? I think it will become minus 3.91. So it can be approximated as minus 4. Okay. So ts becomes 4 divided by zeta. So this will be the settling time of a second order system for plus or minus 2%. Clear? And can be written as 4t, where t is equal to 1 by zeta omega n is the time constant of the system. How we have taken zeta omega n as time constant? For a first order system, what is the time constant? Here, what is the exponent of the time constant you see? It is e power minus zeta omega n t, something like that, right? For a first order system, it is e power minus t by tau. For an RL circuit, you might have derived it as minus RT by L, right? So it will be T by tau. So if you compare this both equation, from this we can get it as, for a second order system, the time constant is 1 by zeta omega n. So if you substitute here, you will get 4t. So the same way, if you calculate for plus or minus 5% band, what will be the relation? Can you do it? What will be the relation? You can write e power minus zeta omega n ds is equal to 0.05. If you do all the exercise, you will get Ts as 3 divided by zeta omega I, which is equal to 3 times T. Clear? So if you move up and feel here, this is 4 by zeta omega I. This will be 3 by zeta. So in problem, suppose this band is not mentioned, you can take plus or minus 2% in a numerical exercise. It is mentioned means you take corresponding to that. So that is the understanding from this. The time constant of the system is inversely proportional to zeta. Right, because T is equal to 1 by zeta omega. The time constant will decrease if you increase zeta. Clear? So these are the important parameters of our first order system, second order system, which you keep in mind. Okay. Now we will do some numerical exercises regarding this. Take your calculator, everything, and keep it with you. Note down this problem. So this is the question. Find all the time domain specification of the system shown in figure. Please write, find all the time domain specification of the system shown in figure. And draw this block diagram. So this is the given model. There is a summing point plus this, and there is a forward gain, path gain, which is 1 divided by S divided by S plus 1, and this is the output. This is the input. And there is a feedback. Since mapping is not there, we can take this as 1, right? So it is a negative unity feedback system. So in order to find, the question is we have to find all the time domain specifications. Time domain specifications. Because all parameters are dependent on zeta, omega d, right? So only thing is we need to, if we know the transfer function of this particular system, we can obtain all these zeta, omega, and omega d, everything, right? So in order to get that thing, first of all, we have to find the transfer function of the given system, right? Suppose this is y of s, this is e of s. You can, how will you derive it? You already know, right? Y of s divided by g of s. So for a negative feedback system, it is g of s divided by 1 plus g of s, h of s. So in this problem, this is our g of s, and h of s is equal to 1. So we can write 1 divided by s multiplied by s plus 1 divided by 1 plus 1 divided by s plus 1. So finally, we will get 1 divided by s square plus s plus 1, right? And so the given problem is a second order system. So we know the planned transfer function. Now what you can do in order to find the parameters, you can compare this transfer function with the standard form. We know the standard form of a second order system is omega n square divided by s square plus 2 zeta omega n s plus omega n square. So on comparing these two equations, let this be 1, this be 2. So on comparing 1 and 2, you get what is the value of omega n? Yeah, 1 radians per second. And in order to find the zeta, you compare these 2 zeta omega n is also 1. From this you can find zeta is equal to 1 divided by 2 omega n. Omega is 1, so this becomes zeta equal to 0.5. So this is what kind of system? Because we already studied the response of the system will vary with respect to zeta, right? Now zeta lies between 0 and 1. So this is a system is an underdamped stable system. Since zeta is positive, we can call it as a stable underdamped second order system. Now you calculate TR, TP, TS, and peak overshoot. These are the parameters we have to find. So first we will see what is rise time. Rise time is pi minus theta divided by omega d. So next parameter you have to find is omega d. Omega d is omega n multiplied by root of 1 minus zeta square. So what is the answer? To become root 1 minus zeta square 0.25. Good. 3 by 2, something like that. That is also radians per second. So how will you find theta? Theta is tan inverse root of 1 minus zeta square by zeta. So please calculate and tell me what is theta. And here it is in degree, right? 60 degree. Yeah. Pi by 3. So see, in this relation, this is in radian. So we have to convert this to radian. That is pi by 3. So TR becomes pi minus pi by 3 divided by omega d. Omega d is 3 by 2. So what is TR? Tell me. 2.41. Yeah. 2.41 unit is second. Now we can find out the peak time. Is pi by omega d, right? So what is the answer? Three point 6275. 3.6277. This will be the second parameter. Now we will move to the third. What is MP? Percentage offset. How will you find out? This minus zeta pi by root of 1 minus zeta square to 100. You substitute the value and find out. because zeta we know it is 0.5, right? So minus 0.5 pi divided by root of 1 minus 0.25. What is the percentage? Yeah, correct. 16.3%. Right. Now we will find settling time, TS. Since it is not mentioned in the band, you can calculate for both. First, you find out for 2%, then you calculate for 5%. For 2%, it is 4 divided by zeta omega n. So substitute the values of zeta omega n and find out what is TS. What is the value of settling time? Corresponds to 2%. 8 seconds. Yeah, fine, good. 8 seconds. And what about 5%?
6 seconds, sir.
6 seconds. Yeah. Good. Yeah. Now we will draw the response according to the time domain specifications. Suppose the system input is an unit step input. Obviously, the steady state value will be steady state value will be 1, right? 1, yeah. We draw this waveform, and there will be some band. Let it be plus or minus 2% and 5%. Will be closer to the steady state value. So if I draw the response, there will be some peak option. This is our rise time. What is the rise time? 2.4 seconds, right? Yes. And this is the peak time. Peak is greater than the rise time. Is 3.62 seconds. This is rise time. Okay. And what about the overshoot? This is the overshoot. What we got is peak overshoot is how much? 16.3. So there is 16.3% overshoot in the output. Which is the settling time? Is the time by system to reach the band without any oscillation. Or we got it as 6 seconds or 8 seconds, right? How much we got? Yeah, 8 seconds. 6 seconds for if it is 2% band, the system is reaching the settling steady state value at within a 6 seconds.
Sir, reverse,
This
sir.
one. Oh, sorry. This is 5%, right? 6 plus. Clear? So hope everyone understood this concept. And, this is a very important topic for the first order system and second order system. Usually you will play with first and second order system. Okay, so next class we will see